Hello, class. This is a successive lecture of the previous session, which is adversarial searching algorithms or adversarial problems, which are commonly referred to as games. In our previous lesson, we have been discussing about adversarial searching algorithms, which considers the opponent to be a perfect player or the opponent to take an optimal action every time. So specifically, we have discussed about Minimax algorithm and its optimization techniques like game pruning, alpha beta pruning, depth limited Minimax algorithms, and alike concepts. Today, we'll come up with another idea, another concept, which makes the existing Minimax algorithm non-functional, a little bit, or suboptimal. So, which is called uncertainty. So today we'll talk about uncertainty in this video lecture, and I will let you read the remaining parts as they are very simple and small. So the problem with the existing adversarial search algorithms like Minimax was its assumption. So Minimax algorithm usually assumes the opponent is a perfect player. So whenever the opponent starts to act randomly, or if the action of the opponent is not known, or if the outcome of a given move is uncertain, then Minimax algorithms usually fail. So for that specific purpose, we came up with this new algorithm called Expectimax algorithm that considers the uncertainties that could happen in a given gaming environment. So today we'll talk about uncertainties in a very precise manner, okay? So when we talk about uncertain outcomes, think of, for instance, dice, a game called dice. So when you throw dice, so any of the dice could turn to one of the sides of it, and you are not able to know which side it is going to turn beforehand. So that precisely or succinctly describes the concept of uncertain outcome. So when we talk about games with uncertain outcome, it's better to think of games like dice, okay? So previously we have been discussing about Minimax, and Minimax is characterized by a game which always considers worst case scenarios, because in Minimax, the opponent is considered to be a perfect player. That means a worst case scenario for the agent. But when we come to the real scenario, opponents are not always optimal. Sometimes they might be optimal, and on some other moves, they might act suboptimally. So for that specific reason, we have come up with a new algorithm called Expectimax, or an algorithm that takes average case scenarios. So in this type of algorithm, here we have a game tree as an example. So the root node is a maximizer node, but the immediate node below the root node is not a minimizer node, as we have been looking at the Minimax algorithm, but it's called a chance node, or a node that calculates the expected utilities, not the minimum utilities. So this is the main difference between the Expectimax and the Minimax algorithm. So the idea is, in the Minimax algorithm, the opponent or the adversary determines or controls the outcomes, because always you are thinking of the actions of the opponent, and your behavior is shaped by the anticipated moves of the opponent, right? But when we come to Expectimax, or average case scenario, where there is no known outcome in the gaming environment, that means where there is uncertainty in the gaming environment, then those uncertain outcomes are controlled by chance. When we talk about chance, we are talking about probabilities, okay? So probabilities are affected by different things, and one of them could be the environment in general. So in Expectimax algorithm, or in environments, in gaming environments where there is no certain outcomes, or where we don't know the outcomes of a given action beforehand, then those outcomes are controlled by chance, not the move or the smartness or the IQ of the opponent or the move of the opponent. So this is one major difference, one other major difference between the Expectimax and the Minimax algorithms. So to summarize the Expectimax algorithm, theoretically, so the first thing is about uncertainty. How can uncertainties happen? Uncertainties could happen because of explicit randomness. In a given gaming environment, the opponents or the environment by itself is filled with randomness, so things may change abruptly, and you are not you might not be able to control them. So one of the idea is explicit randomness that causes uncertainty in a gaming environment. The second one is unpredictable opponents. So in the Minimax algorithm, we always predict the opponent to be, optimal. But what if the opponent is unpredictable? What if the opponent is not strategic sometime? What if it is strategic other time? So such kind of scenarios causes uncertainty in a gaming environment. The other one is actions could fail. For instance, in a given environment where the opponent acts optimally, which is usually solvable by the Minimax algorithm, the opponent might fail doing the expected or the desired action because of different reasons, and one could be a physical reason. For instance, if your opponent is a robot, and if the robot is supposed to go left, but if it will slip because of different reasons, if there is, for instance, obstacle or any other thing, then that slip might change the action of the robot, and that causes uncertainty because it's unexpected move, unexpected outcome. So because of this, value of state calculated at each chance node should reflect the average case or Expectimax values, not the minimum case, not the maximum case, because there is no way to know that in an uncertain environment. So to summarize Expectimax Search, it computes the average score under optimal play. So maximum nodes are the same as those in the Minimax search algorithm. But chance nodes are, again, like minimizer nodes, but the outcome here is uncertain. That means there is a concept of probability while calculating the expected utility of the chance nodes. So the expected utilities are calculated by taking weighted average of children. So weighted averages are further computed by the sum of product of probabilities and value of state of the successor under a given chance node. Okay, so let's do the expected Imax value of this game tree, for instance. Let's assume the probability of occurrence of all terminal nodes downward here is 1/3. That means we have 1/3 for all of them. Sorry, 1/2. Let's say 1/2 because the sum of the probability should be 1. Okay, since there are only two nodes, we should at least say 1/2, 1/2, just for simplicity. Okay, we will not compute for this one for now. So in order to calculate the expected utility of this chance node, we are going to compute the weighted average of these successors. That means probability times value of state of successor for this one, and the same thing for this one. So then we will add the value, the product of this together. That means the sum of the product of the probabilities and value of state of each successor nodes. So in this case, we have, for the first node, we have probability of 1/2 times value of state of the first node is 10, plus probability of the second node is 1/2, then times value of state of the second node is 10. So in this case, we get 5. In this case, again, we get the same value, 5. Then 5 plus 5 is 10. So the expected utility of this chance node, according to these values in this game tree organization, is 10. So you can calculate the same values for the second chance node and take the maximum value from these two. But we'll discuss this one later in detail. It's better to now to have the know-how of the Expectimax search in this while talking about these concepts here. But in the next consecutive slides, we'll do a detailed computation. Okay. So to see the pseudocode of the Expectimax, because previously we have been talking about Expectimax at glance. Here we will formalize it with pseudocodes. So the function Expectimax computes its values conditionally. So it has three conditions. The first one is if the state is a terminal state. So if the state is a terminal state, then the utility is noun, so it will return the state's utility. But if the next agent is max, or that means if the node is a maximizer node, then the Expectimax algorithm computes maximum value of state, as we have been doing in the minimax algorithm, which is the same. But the third condition, if the next agent is expected utility calculator, or rather than minimizer, if it is a chance node, then the return will be the result of the function of expected value calculator or another function. So to see both of these functions separately, the expected Imax algorithm's maximum value function is the same as the minimax algorithm's maximum value function. It assigns the current state of the expected utility of the current node as negative infinity, and it iterates over all successor nodes and tries to select the maximum of value of state among the successors. Okay, so ultimately the return will be the maximum the node with a maximum value of state, or the maximum expected the maximum utility. But when we come to the expected value calculator function, the second function for the chance nodes, it initializes the current value with 0, and it iterates over the successor nodes or the children nodes under the chance node, and it computes first the probability of occurrence of each successor. Then after getting the probability of each successor, it multiplies it with its value of state, and the result will be iteratively summed up to come up with the expected utility value. So the return of this expected value function is the expected utility of that chance node. So to see this by example, the expected value function by example, so let's first convert this expected value function into a mathematical equation. So let's say it's represented by summation of product of probability and value of state of S prime, where S prime is successor state, where S prime is an element of a set which is called, let's say, successor. Okay, sorry for my handwriting. I'm not using a comfortable mouse or environment. So we have converted this algorithm into this mathematical equation so that the computation will be easy for us. So the expected utility of this chance node 1, this is a partial view of some kind of game tree. We are assuming the game tree is very big, but we are considering the one part of that game tree with one chance node and 3 terminal nodes for the case of simplicity, okay? So here we have the expected utility of chance node 1 is the probability of the first successor, because here we have iterator, the probability of the first successor, which is 1 over 2, times the value of state of the first successor, which is what? 8. Plus, because here after this we have iterator here in the outer loop, plus the probability of the second successor times the probability, the value of state of the second successor, which is 24, plus the probability of the third successor times the value of state of the third successor, which is negative 12. So here we have 4, right? Here we have, I guess, 8. And here we have negative 2. So like this. So we have 12 minus 2, which is what? Which is 10. So the expected utility of this chance node is 10. So let's do one more example. Here we have a little bit sophisticated, like it's still simple, but a little bit advanced game tree, and we are supposed to solve this game problem using the Expectimax algorithm. So here we do not have the probability of occurrence of each terminal nodes. So for the ease of computation, we will assign 1 over 3 for each of them, because we have 3 nodes under each node, each chance node. So, assigning 1 over 3 probability for each of them is realistic. So according to this assignment, we have 1 over 3 for each of these nodes. Okay, the same is true for all of these nodes. So let's recall the equation: summation of P times value of state of successor functions, where these successor nodes, where this successor or children node is an element of children's or successors. So this is a fundamental concept behind Expectimax. So to do for C1, for instance, to do the expected utility or to compute the expected utility for C1, we have to first consider the probability of the first terminal node, which is 1 over 3 times the value of state of the first node plus the probability of the second terminal node under chance node 1 times the value of state of the second node plus the probability of the third node under chance node 1 times the value of state of the third node, which is 9. So this is equal to, I think it's 24. 24 over 3 is 8. So this one, the expected utility of this chance node is 8. Let's do for the second one. For the second one, just let's do this simplistically. 1 over 3 times, since for all of them the probability is 1 over 3, we can associate this one like this. So times 2 plus 4 plus 6, right? It's the same as this one. So 2 plus 4 plus 6 is 12. 12 over 3 is 4. So the value of state of the second node is 4. Let's do for this one. For this one, we have 1 over 3 times 15 plus 6 plus 0. Since it is 0, we will not consider it here. Then 21. 21 over 3 is 7. Here we are done, right? We calculated the expected utility of each chance nodes under the root node. The root node is usually a maximizer node. So the maximizer node, as we have already discussed in the pseudocode part, takes the maximum of all its successors. So for this maximizer node, the successors are this C1, C2, and C3, right? So the maximum of these 3 is 8. So according to the Expectimax algorithm, we do have a value of 8 as an optimal move towards the solution where the outcome is uncertain. Okay, good. So we have seen a little bit advanced game tree here, but what if the game tree is very bigger than like this one? So usually in search algorithms, the most important problems were the computational space and time problem, right? So we do have this problem like computational space and time problem in the minimax algorithm, because since both minimax and expectimax are inspired by Deb's first searching algorithms, they do have this problem called a space problem, computational space problem. So for that purpose, we need to apply optimization techniques like memory optimization techniques, time optimization techniques, in order to come up with realistic solutions or algorithms for a given problem. So, but in Expectimax, in the case of Expectimax pruning, the game tree is not a solution, because as we have already seen here, all nodes under the chance node have to be considered along with their probability in order to come up with expected utility. So computing some part of the nodes of the successors of the expected IMAX chance node and isolating or disregarding the other ones won't give you the correct result for the chance node. So for that specific purpose, and because of its sophisticatedness, it's not recommended to prune, or it's not realistic to prune game trees while working on the Expectimax searching problems. But it's recommended to limit depths while working on Expectimax. So it's the same as the depth limited minimax search, but the difference here would be the evaluation function. In the previous minimax algorithm, the evaluation function considers features in order to come up with estimated utility values for the intermediate nodes. Here it is the same, but here the estimated function considers the probabilistic values under the game tree and tries to estimate the values of the intermediate nodes in the given game tree. So by itself, estimating the value of this game tree is a big computational headache, but the concept is you can limit the depth of a given game tree in order to come up with realistic or applicable solution for a given gaming problem, and that could be done by using depth limited Expectimax algorithm. So the function that limits the depth and gives intermediate nodes an estimated value is called evaluation function, and it operates the same way as it used to operate in the minimax algorithms. Okay, so that's all. So the next topic is revising the concept of probabilities, because we have been discussing about probabilities in the previous session a couple of minutes ago, and the people, the Berkeley guys who compiled this slide found it important to revise the concept of probabilities and utilities, and preference and related concepts. So the rest of this slide will discuss about that. So I will let you read that one by yourself and get yourself ready for the exam. Thank you so much.